In this video, we will introduce Newton's second law of motion, which relates the change in motion of an object when a force is applied to it. Newton's second law quantifies this relationship. Consider a following scenario. If you push the box of some mass, the box will begin to move with some acceleration. If you push it harder, it will accelerate faster. If you push it lighter, it will accelerate less. Secondly, if you push a heavier box with the same force, the heavier box will accelerate less than the light box being pushed by the same force. Newton's second law explains this observation by saying when a net force is applied to a mass, it causes the mass to produce an acceleration. This law is captured in the following formula, which states that the net acceleration is equal to the net force divided by the mass. Note that in Newton's second law, it is the net force that produces a net acceleration. Sometimes, a mass can have multiple forces acting on it. It is the resultant or the net of these forces that produce the net acceleration. If all of the forces cancel out and there is no net force, then there is no acceleration and the mass remains in its current state in accordance with Newton's first law. So if an object is observed to be at rest, what can be said about the forces on the object? According to Newton's second law, if you double the force, then the resultant acceleration is doubled. If you double the mass, then the resultant acceleration is halved. So acceleration is proportional to the net applied force and inversely proportional to the mass. This formula is consistent with our observations. Consider the same force being applied to different masses and their accelerations measured. Which of the following graph would illustrate the experimental results when the acceleration is plotted as a function of mass? Newton's second law is also commonly written as the net force being equal to the mass multiplied by the acceleration. Now the SI unit for mass is a kilogram and the SI unit for acceleration is meters per second squared. So the product of mass and acceleration gives us the unit of kilograms meters per second squared. But this derived unit is quite a mouthful to say each time, so a simpler unit of the Newton is used instead, where 1 Newton is equal to 1 kilogram meters per second squared. Another thing to note from Newton's second law is that mass is a scalar, but acceleration is a vector. The product of a scalar and a vector is also a vector. So therefore, force is a vector and has both a magnitude, which gives the size of the force, as well as a direction. The net force will be in the same direction as the net acceleration. Consider an apple falling to the ground from some height. As it falls, it is experiencing acceleration due to gravity at a rate of 9.8 meters per second squared downwards. It will hit the ground with a force given by the product of its mass times the acceleration of gravity. If the apple has a mass of 200 grams, then the force of the impact on the ground will be 200 grams or 0.2 kilograms times 9.8 meters per second squared, which is 2 newtons. So what will be the force of impact of a 2,000 kilogram car? In summary, Newton's second law states that a force applied to a mass produces an acceleration, or when a mass is accelerated, it produces a net force given by the mass times the acceleration. The animation used in this video was made available from the PhET Interactive Animations project at the University of Colorado. You can open the animation by clicking the animation link in this module within VU Collaborate. I would encourage you to play with the animations to be more familiar with the force concepts. Remember to turn off the friction for the time being until we introduce it later on.